Hello Applied Math students. In this video we are going to talk about phase 1 of the Mathematics on the Moon project. I will not be reading every step of it for you. You have paper for that, but I'm giving you the basic ideas of what you're supposed to do. You may work in groups of 2 to 3 people. We're going to create a scale drawing to model a real-life problem and apply the Pythagorean theorem in phase 1. Phase 2 will apply distance and rates, and we'll analyze data to find a solution. So let's begin. Okay, here's our background information. We're on a mission planning team that will determine the best route for the crew to use on the first trip using the new pressurized lunar roving vehicle. This exploration mission will include gathering rock samples from around the moon's, I'm not sure if I'm saying this right, Daggerlash crater. Rover 1 is at habitat A on the map, which is down here, near Shackleton crater. Its mission for the day is to drive to the rim of the Daggerlash crater to collect rock samples. Rocks can be collected from any point along the edge of the crater. That's segment PQ. Before Rover 1 and the crew return to the habitat, they must also stop at location B on the map, which is up here, in order to reset a seismic sensor that has been gathering data about the interior of the moon. All distances are denoted in this problem. These are going to be significant amounts for us, the 28.5 kilometers here from point A to point B, and then 19 kilometers here up to Q, and then 17 kilometers over to B, and these are 90-degree angles here. So, we're going to create a scale drawing of the mission on the graph provided that's below on your page. It's next screen for me. We're going to start off by locating point P at the origin. So you will want to put point P here at the origin. That's point P. And we will want to have segment AP lies on the x-axis. Now going back to our image, we can see here that segment AP is 28.5 kilometers long. So when we put that on our table, we want it to be right here. This is point A. It's located at 28.5. Now we're also going to put in our other points. We're going to put in Q, which is 19 kilometers up from our point P, and B, which is 17 kilometers over. So we need to place those appropriately. Here is our origin point, and Q is 19 up from there, and then point B is horizontal with point Q, and it's 17 kilometers away, so we would need to put that at 17, 19. This will be point B right here. So first thing, you need to put those points on your graph. Then you're going to choose a random point on PQ along the crater that you think would give the shortest total distance, and label that point G for guess. You can put it anywhere along here between P and Q. Each group will probably have a different guess point, but pick something. Pause the video while your group thinks about what you guess will be the shortest distance. There is no penalty for being wrong, so it's okay to guess. Okay, now, using a colored pencil and a straight edge, plot the point C at 0, 3 on segment PQ along the crater where your crew will gather rock samples. Draw the path of Rover 1 from A to C, then to B, label your points accordingly. So we're going to do this together because everyone's project should have this same point, C, 0, 3. So 0, 3 is right here. Here is point C, and then we're going to draw our path here. You will use a straight edge for this. We're going to go from A to, let's see if I can do this right. We're going to go from A to C. And then we're going to go from C to B. Okay, so this is the path that we're going to take, and we're going to calculate the distance AC and CB. We're going to find the total length of AC plus CB. We need to make several calculations using the Pythagorean theorem. Okay, we're going to do this together. You're going to work with your mission planning team, and you're going to plot 4 different locations along the y-axis for point C. We're going to calculate the point C at 0, 3. I want you to choose at least one point with a fractional value for y. Choose something with a 0.5 and draw the paths for your mission graph. Use a different color for each path. You're going to end up with a total of 10 segments. there will be 2 of one color going from A to some point, and from that point to B. Then you will have 2 of another going from A to a different point, and from that point to B. And so on for 4 different points besides C that we're going to calculate right now. You're going to enter the corresponding data in the minimal path table, which is on our next screen. So, okay, we chose the point 0, 3. And so now we're going to use that to calculate. I want to show you how we're going to use that. We are going to be using the Pythagorean theorem. And the way we're going to do that, let me see if I can highlight. You know, we're going to do this. We're going to use this right triangle formed right here and here, and then our A to C. And that is a right triangle. And we know how long this edge right here is, because from P to A is 28.5, and from P to C is 3. So we will come over to our table. And since we chose 0, 3, then PC is 3. CQ is going to be, okay, we're also going to find another. We're going to calculate this distance here from C to B, and we're going to use, oops, sorry, can't draw a straight line. We're going to use this and this and CB, so we have another right triangle here. So we're using the Pythagorean theorem a couple of different times. Now, in order to find AC, we would find this this vertical leg plus this horizontal leg. We would do A squared plus B squared. That would give us C squared. So in the end, to find C, we would need to take the square root, which is what this table is showing us over here. That when we chose the point to be at 0, 3, then our PC is 3. CQ is 19 minus 3, because 19 was our topmost point, which gave us 16. Then to find AC, this distance right here, this 28.5 is always going to be constant, because from A to P is 28.5. But PC is going to change depending on what we have right here. We'll put that in, we'll calculate it. Then we'll find CB, which, going back, CB is going to be this hypotenuse right here. So we need this vertical leg and this horizontal leg. We'll square this leg, square that leg. That'll give us C squared, and we take the square root in the end. So for this, we use this 17 is still going to be constant. That is our horizontal leg. And the CQ is going to change based on this number right here. Please round to the nearest hundredths place. Once you have these values, then this is your AC right here. In this case, it was 28.66, and CB, which was 23.35. We add those up, we get 52.01. Now on my graph, I didn't make that a nice color, so for me that would be black, and then I would use a different color for my next points. Each point we pick, these values are going to be different. You know, whatever number we pick right here, that number is going to be PC, and then this one will be 19 minus whatever that value is right there. Then we plug in PC right over here into this column, along with the 28.5. We plug in CQ into this column, along with the 17. We get a value for AC, whatever we get here, and CB, and then we add those values up over here. Tell me what color that is on your graph. You're going to do that for 4 different points. And in the end, for this 0n, these are still going to have n's. These are not going to be numbers. You're creating a formula for how to find a general formula that you could plug any number into. So these in the last row will not be just numbers. There will still be an n somewhere in them. After you've had a chance to do all that, you will get a colorful graph. You will have 10 segments in 5 different colors, and then work with your team to answer these questions right here. And then our next stage of our project, we will be talking about distance and time. Okay, if you have any questions, ask.